All right, hello everybody, and welcome to Malware Club. So today, the main thing the main agenda for this week's meeting is we have a guest speaker with us, Micah Flack. So Micah Flack is currently a student, a PhD student in the Cyber Operations program, and also he works as a researcher in the Idaho National Labs. Also, he was our president last year, actually, for Malware Club's first year. Last year was Malware Club's first year, so he was the president last year. So he's going to be presenting on symbolic analysis. And so, yeah, just before that, I guess I'll just announce that we're also going to have a meeting next week, the 30th. So this is sort of like a bonus meeting. And then next week we'll have a meeting. And then following that, we'll have like meetings again every 2 weeks. So I think there's going to be, I believe, 2 more meetings. So, yeah. So yeah, I'll hand it over to Micah if he's ready.
Sweet. Can you guys see that all right on Zoom?
Yeah, I can see.
Yeah, so like Odin said, my name is Micah. I'm going to present to you guys today about symbolic analysis. Then there's a couple slides at the end about library code emulation, just slightly related, should be interesting. Just kind of recapping the introduction that Odin gave me. I'm a researcher at Idaho National Labs, and I've been going to DC for quite a while now. So it's good to see new faces because I haven't been on campus in a year or 2. So just kind of getting into it then. So the main part, doing malware analysis, the 2 things that, most people are familiar with is static analysis or dynamic analysis. And for the most part, I mean, that's the whole malware analysis role for people. But there's actually 3 other ways that you might get into the further along you get with malware analysis. That's SDA, CDA, and code library emulation, or symbolic analysis, and CDA, which is Concolic. And Concolic is actually just an abbreviation for concrete symbolic. And we'll get into why that is in a couple of slides. As for the funny face, the smileys, that's the logo for Angr, which is a symbolic analysis tool you can use. Kind of goofy, but it's kind of funny. So there's a couple examples that everyone's familiar with. Static analysis, you might use a tool like CFF Explorer to just kind of browse the portable executable structure for a binary, or you might even open it up in something like this. This is what I use. It's called Clutter. So it's a graphical version of Radar. And then for dynamic analysis, something you might do is opening into a debugger and just running it and trying to get a more behavioral or heuristics idea of how the samples behave. And then when that, you can't really see because this is a terrible screenshot, but you might even do something like API monitoring. This is actually my first time using the tool because I wanted to get a nice screenshot for things you could do. And it actually took me quite a bit to figure out how to use it. I don't know if people can see this on Zoom, but when you actually submit something for this tool, it'll show up in this pane, and then you'll click around and you'll kind of interact with the software, and you're not going to see anything over here. That's because if you actually want to do any API monitoring, you have to go to this leftmost API filter pane. You have to select things within the category you want to look at. So like, I don't know if you're trying to see what kind of like networking API calls are being made, you would select wireless networking. And then any functionality used would actually show up here in the monitor capture. So that was something I just played with to get an example of the slides. It's actually pretty fun. It actually does tie into the code emulation part later. So a little more about what symbolic analysis even is. So before you can even use symbolic analysis, you have to use symbolic execution. So before you have symbolic execution, you actually have just how you would normally execute a program. So it's like dynamically, where you would just run it, it gets loaded into memory, makes all calls it needs, and generally does what software does. But what symbolic execution does is it takes a disassembly of the binary and then tries to symbolically express all the paths it would take. I'm just gonna skip a slide so I can explain that a little more. So like with explanation, you're gonna see something like this, which is a graph, or some cases it's called a CFG. That's a control flow graph, and how it flows from control block to control block to, and so on. So when we say that something's being symbolically expressed, we're kind of just explaining how here it's kind of terrible which one. When you do execute something, you go through each block, and then you have conditions that need to be met to then go further down into either path. So you have this path, and then that path, you could go here down this branch, and you can take that one or this one. So to express something in symbolic execution, you're simply saying that instead of running the program normally, how you would, you're going to express it in terms like this call graph, and then each path you could take, and the conditions that need to be met to take those paths. So it's kind of a rough explanation. And I should also probably say, so when you do run a program, you usually provide some sort of input. So if you were to, if you had a program where you passed in, it was just going to like print out a statement, and you ran the program and you provided like hello world, and then that program runs and it goes print, and then the argument that's provided, that argument would be a constraint required to run that program. So if you do a symbolic execution, you're not actually taking that input and running it. You're expressing that argument as a symbol, and which is kind of like what you see here in this graph, where if you remember like old algebra problems, where you're say like given the problem and explain for X and Y, that's kind of how these control graphs get explained. And it tends to end up looking like a muddy math problem. But some of the advantages over doing that compared to sort of a dynamic analysis is you're not actually running anything on your system. It's kind of like how, like, terrible metaphor, but you have SpaceX, and they're more of like an iterative design. They send rockets up, they explode, and they come back down. That's like dynamic analysis, where you can run the program, it might blow up, it might brick your system, but you get an idea for how it works. Or you have the more theoretical and mathy way of explaining things, where you try to figure out what the requirements are for a problem, and then explaining each step, which is more or less how symbolic execution goes about it. And then something I should also say is that for one of the cons with symbolic execution, a lot of times when you're doing malware analysis, you have things like jump tables. So it could be sometimes in reference to like call EAX. And call EAX could be dependent upon some kind of input that's provided either by the system at runtime or just through user interaction. So a lot of times that's just going to end up getting expressed as a symbol. So I should probably also clarify. A symbol is like X, Y. It's like a variable, and it's empty until you actually assign value to it. And con being that if you can't actually see what values are being stored in those symbols or variables, then you can't actually like fully determine what the results or output is going to be. And then there's this example that we flashed by. So typically, there's more steps on this arrow, but you have source code for the program you write. And this is kind of like some C pseudocode. And then you have arrow, magically you get a CFG. But usually, and this isn't actually how like CFGs are normally actually referenced. This is more like what you're going to see in a textbook when you look up control flow graph. But I mean, it kind of gets the point across. You go from source code, you compile it, you get a binary or an executable, and then you load that executable into your symbolic execution software, which disassembles it and then produces a CFG from there. The other image we showed, this being the graph or control flow graph you're more familiar with. This is just produced with Cutter. So, and then you get to the terms symbolic and concolic analysis. So again, the sample gets compiled, and then you load it into your software, it gets disassembled, and then from the disassembly, you start to sort of match up what the blocks are for that code. So going by things like the calls, the jumps, comparisons, rets, those all determine what the graphs end up looking like in each individual block, and then how they go from A to B to C. So the symbolic analysis input variables in place of concrete static values. So how the symbolic analysis differs from the concolic or concrete symbolic analysis. With the concolic, you have statically defined values. So it's like when you make a call to a function, when you define it, you say like print. So you have print, and you have the first variable, second variable, third variable. So instead of saying like var A, var B, var C, you actually define static values to be used. So for print, a concolic version of that would be print hello world. The symbolic version of that would be print X. And then X is dependent upon whatever inputs provided. And then also another part being about what makes it concolic or concrete is that, I'll pull up the image, or do I have? I was going to draw it, but I'm a terrible drawer. So, so if this were, say, like a symbolic analysis, symbolic would say that when you get to doing a test EAX, they wouldn't be registers per se, but they would end up being symbols. So EAX would become like the symbol A, and then you would essentially be doing hypotheticals of those comparisons. So, so for symbolic, you would say test EAX, or like test A to A, and then assuming that it meets the constraint, so a jump equal, then we would say, given the constraints that A is equal to A, we go this way. And that's one path you could take symbolically. Or assuming that A is not equal to A, you would take this path. Whereas concolic is concrete and statically defined. So it would be more like saying test 0, 0, they're equal, so we take this path. We don't consider this path because that doesn't meet the constraints that were established here in this block. And then also, because it's concolic, if you don't meet the constraint requirements for each time you reach that flow control, then this is where it would just stop. So it's like same way, same limit you have with like dynamic analysis, where like if you're doing a capture the flag or something, running it, and then you get to this flow control where it's like it's asking you to provide the flag. You don't provide the flag, you provide an incorrect flag, you take this path, and you don't get the answer because you provided incorrect input. You didn't meet the constraints that were required to take that path. You only end up taking this path. So if you have to think about it in other terms, like if you've taken algorithms, you could express it as like binary tree, where like you have everything branching off into different nodes. Symbolically, you would be traversing like each node and going the full path, and then going, with each branch. And concolic, you're only going down like one branch and then the like single leaf, which is what I was gonna try to draw. So it's I don't know, this was terrible metaphors I came up with really late at night. So dynamic analysis, you'd be kind of just like chucking the marble, seeing where it lands, or observing how fast it falls. Static, you weigh the marble, you maybe look up similar marbles on Google. Symbolic analysis, you take that marble and you would do the like math for it. So you'd weigh the marble, I don't know, I never took physics, so that's probably a bad example. But you would, assuming you know how much it weighs, like air resistance, how fast it's going to be chucked, you would do the math to then tell you, given those constraints, like how far it would go without actually chucking it. And then concolic analysis is saying you go like this specific angle, this specific speed, what like specific location does it end up at? So it's concolic is like one very determined path, and then symbolic is considering all paths if you meet all constraints for each individual path. So then you're probably wondering, how do you actually do symbolic analysis? Like reading about it's fine, but what tools would you need to use to actually do it? The one that I'm most familiar with is using Angr, and Angr is it's like Python library that you can use, but it's a multi-architecture binary analysis toolkit with the capability to perform dynamic symbolic execution and various static analyses on binaries. So Angr is actually like multiple parts. It provides the emulation that you need to load and disassemble the code, which is a part of the underlying unicorn engine that it uses. And then in other parts, I'm kind of getting ahead of myself. But it also uses a CLE loader. So when it gets to the symbolic execution part, it knows like what regions of memory it gets loaded into. Which is complicated. But some other alternatives you might use instead of Angr, if let's say you didn't want to do, and they do different things, but you might use PE file or life, which would give you more like structural information about the binary, which you can do with Angr. You don't, because it has the code emulation for the binary. Angr does multiple parts, and PE file and life are just one part of it. But there are other options you can use for that. But what does make Angr more useful is the fact that we can do the symbolic expressions for the binaries, and the different paths that you would take from like one block to another block, so on. But everything has its limitations. Like with PE file and life, you can't do symbolic execution. You're just you're doing a static analysis and you're saying, well, it has these imports, it has these exports, it has like these sections, like .text, .data, like that's all PE file and life can do. The limitation for Angr is that if you have like a single block and you're recursively referencing it, so because what Angr does is it goes from block to the next block to the next block to the next block until it reaches like that terminating block within that path. So if you have something that's just going to recursively keep going, kind of in a loop, it's kind of like if you write a program where if while 1 equals 1, do this, it's kind of the same thing where you're just kind of like endlessly going down. That'll crash Angr because it'll never reach that like end block. Ran into that quite a bit with some Linux libraries when I've tried processing them with Angr before, which was kind of interesting. You can actually go onto their issues page on GitHub, and that's something they've known about for a couple of years, and they refused to fix, which is fine. But so kind of just real quick here, how do the binaries actually get loaded? So this is kind of just general, but it gets loaded in through project.loader. It uses CLI loader, and it tries to like if you're going to load it into X32 debug, and then you get like the entry point for it, it gives you like a virtual address in memory, so you know where to reference it. That's what CLI loader does, or at least that part of it. And typically, I mean, when you load it into Angr, use CLI loader, it will just rebase it in memory to like 400000 hex. And then that's kind of like the object representation of it. So then anytime you were to traverse like the PE structure for that binary within the CLI loader object, it's all going to be starting at that offset. So it's in reference to that. And then you can get more of the PE structure sort of analysis that you do, like with PE file or life, just pretty basic. We can query here, like you can see if it's position independent, and you get like true, or does it have an executable stack, false. So it does all that analysis when you load it in. And then, yeah, so when you do symbolic execution and then the symbolic analysis, you have to have a solver engine. So a lot of times it's called like a SMT, but it's what will produce the CFGs, or in some cases it's also referenced as like a abstract syntax tree, which is more like that textbook sort of graph example we showed before. where this is it's a CG, or it's a abstract syntax tree where it breaks everything down between each block. But what the actual part that Angr plays, because you have like CLE loader that loads into memory, you have the Unicore engine that does more of the emulation for the binary. The part that Angr plays is actually doing the abstract syntax tree production of it, where once it's been emulated by Unicorn and then loaded by CLE loader, Angr then does the engine solving so that it can express the paths from each of the blocks and as an abstract syntax tree. And part of that is choosing the symbolic values. So it's kind of complicated. If that doesn't make sense, I should probably explain that before I go further. If anyone has questions about that. This kind of explains the state solving better. So it's always better to use examples. But so the state solving would be like where, so you add all these constraints and then you evaluate it. So you have the symbol X, the symbol Y, and the constraint where X is greater than Y. You have the next constraint where Y is greater than 2, and the third constraint where 10 is greater than X. And then you tell the state solver to evaluate for these constraints what X is equal to. And it will consider all the options for X and Y until you get the value for those symbols that meets the constraints, which in this case is 4. So, and this is a much more simplified example, but this is essentially what it does with registers or even the regions in memory. So some of the potential applications you might use this for you could use it for code audits, exploitation development, causing binary capture the flags, or even malware analysis. And I can kind of explain each. So code audits, one, if let's say you didn't have like the source code, which usually if you're doing like a code audit, you'd actually just reference the different functions between each release and would say, like what actual changes were made in source. But where you would actually do that here with Angr is if you had the actual executables or binaries after everything's been filed, you don't actually have source code. You would use Angr to do like control flow graph comparisons of each. And there's another component that I didn't explain because it would take forever, but there's an intermediary language representation. So when it expresses all of the instructions or registers symbolically, it will use it in a intermediary representation. And the one that Angr uses is called vex. So you get all of these vex symbols and you get symbol counts for those symbols. And based off those symbol counts for each control flow block, you would do comparisons for the address it's loaded in at for the binary with the symbol counts in reference to another executable. And then based off that, you could say how similar or dissimilar the samples are, which is kind of confusing, and it's actually very resource intensive to do, because not only do you have to like load binary into Angr and get it all set up, and then also do the symbolic execution and then symbolic analysis. You then export it as its intermediary representation. And then after that, you also have to write a solution to compare each of the block symbol counts to each other to then say how similar the functions are. And it is one solution you can do, but, and I've done it before, but it's also not that much better than just opening up the radar, doing radar diff with 2 samples, and then it produces effectively the same answer in like 5 minutes, and you don't have to program anything. Where I do think you might have more better uses for it would be like with the capture of flags or malware analysis, because we do have an example, but my environment's going to work, so I can't actually show it. But with capture the flags, so it was kind of like alluding back to the previous example, but if you're looking at like the control graph for a capture the flag or whatever, you can load the program into Angr and you can use Concolic analysis. And when you get to the expressions where it would require user input, you could simply just kind of like iterate through different values. It's kind of like more like fuzzing, but you can sort of dynamically run it in the sense that you get to this comparison. Then you statically set values, or in this case, you might even just like loop through it. And then you do that as you get to each block. And it'd be kind of like if you just opened it in X32, set breakpoints at the offsets you want. And then when you get to the comparison, you just like change the values and the registers or in memory. But with Concolic, you're not actually physically running the executable. You're just going through. It's smoother. It's the best way I can say it. Because if you were to do it in like a debugger dynamically, there's everything else leading up to that point. So unless you were doing it same way you do with Concolic, where you're making sure that the right inputs are provided at like each checkpoint or each breakpoint, then if you're doing it with dynamic, you're going to end up breaking something along the way because you're just not going to have provided the right inputs doing a debugger, because you won't actually know everything that you need to change at each breakpoint to make sure that it runs cleanly. If you're just in a debugger and saying, oh, I want to change EAX to this value or change EAX to this value, you'll then get to this one, or much further along the line, you'll get to another if statement or comparison where the constraints for that aren't going to be met because you didn't initially provide the correct input here, and then somewhere in between it got messed up. So to do it as effectively with the debugger, you would have to be controlling the inputs at every block to make sure you're getting the exact input then for the rest of it as you traverse that path. Whereas with Concolic, you're kind of already doing that naturally because you go from block to block to block to block, and you provide the inputs as it goes through that. Hopefully that makes some sense. So I can kind of show this one. So this is kind of just a CTF example that I'd found before, but it's kind of a little better than what I tried showing. So like here, you go into main, you provide RC, RB, you have your buffer, your message, it says printf, enter password. You provide the password, it gets entered into the buffer. And then you have this other buffer that's defined, and I would have to go to the other script. I'll kind of explain that real quick. But the length user def is just another flag that's provided, and the author tries to make it so that it's just like a randomly seeded thing, so that you could just run the challenge multiple times and the answer won't be the same. So people can't just like copy and paste and say, "Oh, I did it." But if we were to not do the seed, for example, the user def that was referenced is just this like A to Z all the way to Z. So I'll go back to the other one, but we'll just kind of assume that's what it is. So assuming that the user def in reference there is just D all the way to Z. Then we have buffer at I equals complex function, which goes all the way up there, and it does comparisons of I, so from the for loop to the buffer. So then eventually, assuming it passes through here, after the complex function, then you get to where the string comparison buffer to user def, which is just, again, ABCD all the way to Z. If it's not, we get try again, else, good job. So the idea for this, if we were to do symbolic execution, we can look at their scaffold. So they do provide some explanations. So if you want to go back and look at this more, you can. They actually have, I should probably show that real quick, but this is a whole Angr CTF. So if you really decide that you like symbolic analysis and none of my explanations were that good, which they probably weren't, you can go back here and you can start off at the 0 and go all the way through, and they're all different challenges, like doing symbolic stacks, registers, memory, dynamic memory. If you want to do symbolic files or hooks, which would probably be a good one. They're all different ways, actually even shared libraries. They're all different ways you can learn how to use Angr. Really good. We'll go back to the other one. So this is kind of to show how you would actually use Angr. So once you've imported it, you would do angr.project, load the binary in, and then you do project.factory entry state, and you have to provide the options that you want Angr to use when it does the symbolic analysis, or I guess at this point this is symbolic execution, but you're telling it to fill unconstrained memory and registers with symbols with Angr, and the entry state again is just tells it to start at main or entry within it. And here you do the simulation manager, so bringing it to the initial state, which is what we created here. And then print good address. So the good address here for the binary is supposed to be, so we'll go back to the actual source code for it. But this is assuming you've compiled it and you have like a executable of this, and you want it to find the path and constraints that get you to printf good job. So assuming I had a good environment to show you this with, we would compile this and then we would open it into like X32 debug or IDA. We could probably just do an IDA. And then we would look for where this call is within the program once it's been loaded in. And you could, like if you were in IDA or if you had it in X32, you probably just do IDA. You'd get the offset that you can use in IDA. And then you would just take that offset and add it to whatever the rebased address is. So if this is like 2000, if the offset for this is like 2000x, then the address you would provide to the Angr script would be like 42,000x. That's the address. Oops, I went to the wrong one. So what it does then is it does simulation.explore, find, and it tries to symbolically execute the program until it reaches that address you've provided. And then assuming it's found, we grab there from the simulation object, solution state, and then here it'll just print the string that it found. Kind of one of the more basic examples you can get for the symbolic analysis. It's complicated to play with, but so just to recap, it explores the address, finds the address, and in order to get there, it also gets all the constraints needed to go, essentially from like block A all the way down to block Z. And then once it's found all those constraints, or in this case, it's just a string, it'll print that out. So had we compiled it and ran it in our environment, the thing that it would print out here would be the password that you provided when it asks for it. Which, in this instance, assuming we didn't provide like a seed or anything, it would just be like ABCD. That string there would be what Angr would spit out. So that's the more complicated part of the presentation. And then the more fun part is talking about code library emulation. So instead of doing the complicated symbolic analysis or dynamic analysis, where you could detonate it and then blow up your environment, you can do library emulation. So the actual libemu or library emulation that everyone references, you normally would have found at the site git.carnivore.it. But when I went to it, the domain is for sale. So I went on and I found a reworked version of it, which is just called SCD debug. It's actually included in Flare VM already under the debuggers. But the SCD debug uses Unicorn engine. which is the same one that Angr uses. And this here's an example that I did real quick, some shellcode I had. So if you do the /f flag there with the shellcode file, it will rebase it and then load it in. From there, and this is the example output. So you've got like an API call to load library A, and this is the input that's provided when it's called. Gives you the supposed offset from the rebase. So this is 43 bytes from there. And then you have URL download file A URL provided, and the file name it would be outputted as. Then you have one exact sleep, delete, and so on. Actually show this because I have that working. Yeah, that's why I can do the Angr demonstration, because I'm having some issues there. Okay, so this is Shellstorm. So it's just a collection of different shellcodes we can use, and we have it for a whole bunch of different platforms. So BSD, FreeBSD, Linux, the different architectures. But we're just going to do a Windows one. Find one that's actually just shellcode. This is the part I did not prepare ahead of time.
The one for Serenity. It's pretty short. It's like 112 bytes.
Check this. This is Python scripter dash. Does anyone know what that's written?
It's in, but it's,
That one, I don't know. That's written in Bash.
yeah, so it won't see.
I think the problem is that if you look at your file, you've included too much stuff at the top.
Yeah,
Maybe you should
maybe
keep
just
colon
use
slash
the-
slash.
just use the hex part of it.
Yeah, just a hex file of it.
It's in Python, and the M3U file has actually got the binary. Were you looking for the binary part of it?
Oh, I just wanted
If
to.
you ran it, it probably created the M3U,
That's what you tried doing.
but I think it's Python too.
Yeah, it's just, I don't know that one. Yeah, it'd be like, yeah, that would be very good. Probably. Some, three.
The way the guy that did that one is specifically. doing that.
Yeah.
Okay. It's one of the three examples out
I do have the one I showed on here, so I'll just do that. It actually wants to show the show code example, but you have a clear view on focus here somewhere. So Flare VM, it's just under debuggers. And it's just SED. Or SED. That's by originally the VMU called Nature and Marcus Coder. And the rewrite here that uses the VMU is by a guy named David Zimmer. And you can actually do a lot of with it, but to just get the output that I showed you. You just do the /f flag. There you go. Well, flash. I can't. So it's pretty much that easy. So it's just a joke, but anybody have questions or answers?
I do have a question.
Yeah.
So when you're using Angr, are you able to, when you're comparing the binaries, are you able to use that for threat actor? Being able to detect threat actors on specific binaries. So let's say I have malware XYZ that's run by like the Conti ransomware group. Would I be able to go through and take that and then compare it to previous examples and be able to find, oh, hey, this is Conti?
In a limited sense. So it's a little easier to demonstrate if you're looking at something that's very vanilla, like Ubuntu libraries, because the iterative changes they make are very small. So
Sure.
if you were to do like the VAX intermediary representation, to generate those symbol counts for the blocks within a given function. And if it's a function that has been written by Conti and it's been used like they literally use it for opcode. This sample A, sample B, then yeah, you could probably like within like 80-200% say that they're similar.
Oh, that's kind of cool. Okay.
But if they are doing anything different, like if they're if the implementation isn't the exact same, like if they're doing the same thing, like methodology is the same, like it's the same idea, but it's actually being implemented differently, then it's not going to be an exact match. Just because the order of the opcodes and the instructions when you run it through Angr, it's going to be very different. Like, I mean, maybe if you do just like the abstract syntax tree or a CFG, and you just compare like the flow of each, you could do it that way too, and you might be able to say that they're more similar that way. You can't really rely on just doing like instruction to instruction with Angr.
Okay.
Because it'll just get confused that way.
Gotcha. Cool.
Thank you. Any other questions? Yeah.
Okay, kind of like that one. Let's say instead of analyzing malware, you wanted to compare two binaries to like do a patch diff. You wanted to say like this function adjusts by 4 instructions. So maybe the exploit we're looking for is in those instruction changes. Do you think Angr could be used to do that? Like Ghidra has live tracking version and it's pretty good. But if you like adjust one thing and then the CFG goes haywire because your jump table is messed up or something, like then it doesn't know that that's the same function. Do you think Angr would be good at that? Or
it depends on how much it changes the actual like overall function, like structure of it. If it's just like 4 bytes, but the function itself can still be like recognized, then it should still match. Where it might fail would be like different API calls, like if you're doing like create file W versus create file A, or it relies on any sort of inputs that get generated from like a jump table. So like that sort of stuff might change it, or offsets on the stack might alter it. Kind of like if you were to like do EBP minus 16 here, and then like in another location you're doing like EBP minus 64. If there's like a mismatch there, it might get confused. A lot of times it can be kind of case by case, but it should still match it.
because I've seen Ghidra get confused at like stir copy versus stirring copy. You've got one additional stack parameter, so then it gets confused, even though the jump happens or the call happens in the same spot. It was really confused by the stack setup.
And it just says it's like a garbage function or doesn't even get loaded.
Yeah.
Yeah, I've had stuff like that happen with Ghidra. And I just don't use Ghidra, and then I use Radar instead because it does it a lot better. Yeah.
I didn't hear what you said. What do you use instead of Ghidra?
Oh, okay. I use Radar. Or some people like to call it Radar for whatever weird reason.
Radar. Okay. Awesome.
Any other questions, or otherwise it's been a very long presentation, longer than I meant. Cool. I'm good there then. Thank you all for letting me present and share this with you. Any questions about links? I can send them to you.
All right, yeah, thank you, Micah. So yeah, the next meeting we'll be having will be next week, the 30th, and the topic that I have planned then is like malware analysis of like a .NET malware is the currently planned topic. So yeah, we'll see you next week. Thank you, everybody.
Thank you.